are two different kinds of special right triangles that you may want to be aware of as you're doing various problems, usually involving trigonometry, sometimes just Pythagorean theorem problems or other kind of general geometry problems. Both of these special triangles come from cutting apart a regular polygon. So a regular polygon has all sides the same, all angles the same. And certainly you've seen many, many triangles in your life that don't meet this criteria. Their sides are different lengths. Their angles aren't all the same. But let's start at looking at the special triangle that comes from a regular triangle. So a regular triangle has a more specific name. Because everything about triangles, we've got a ton of names. We call that an equilateral triangle. That's one where all the sides are the same and all the angles are the same. So I'm going to draw one, not to scale, but just kind of doing my best. And you can see here, this is not a perfect triangle in terms of being equilateral. This side is a little longer than the other ones, but that's okay because it's just going to be my model here. And in an equilateral triangle, all the sides are the same length, which I'll call S for side. And all of the angles are the same. And since every triangle adds up to 180 degrees, I can figure that out by doing 180 divided by 3 and know that each of these angles is 60 degrees. So as long as I have an equilateral triangle, if I know one side, I know the other two sides. And as soon as I know it's an equilateral triangle, I know all the angles are 60. So we don't usually have to throw a lot of our triangle solving tools at a situation with an equilateral triangle. But we're talking about special right triangles, and this isn't even a right triangle. But I can construct a right triangle from this vertex through here. Since this is an equilateral triangle, this will cut this exactly in half because it has symmetry over this point, over this line. So since it cuts it exactly in half, that would mean this little chunk here, that's part of my half equilateral triangle here, would be 1/2 S. But that's going to be kind of annoying because I know where I'm going with this. So I'm going to use a different equilateral triangle that's this one, but zoomed out and with a zoom factor of 2. So this is a dilation of my boring equilateral triangle where I've multiplied all the sides by 2. That wouldn't change my angles. It's just twice as big. Whatever S is, it's 2S now. And the reason I've done that is so that in my right triangle, this side can be S rather than 1/2 S, and I don't have to think about fractions while I'm doing this. I could think about fractions, but why would I if I don't have to? So I'm just being strategically lazy in how I do this to avoid having a fraction there. So here is my right triangle that came from cutting my equilateral triangle in half. This is a right angle because this is a perpendicular bisector of that side. This side is 2S, and it's the same length as the original equilateral triangle. This is 1S, I want to know what this side is. So I'm going to call it x, because that's what I call things that I don't know. If I don't have another idea what to call them, I call them x. And this is still 60 degrees. This is 30 degrees because it cuts this angle in half. And this is, of course, 90 degrees. So this is a 30, 60, 90 right triangle. And this is the first kind of special triangle we'll be looking at today. So using the Pythagorean theorem, I know that this side squared plus this side squared equals this hypotenuse, side across from the right angle squared. So I'll set that up as s squared plus x squared equals 2s squared. And I had to put this in parentheses because it's 2s times 2s. It's not 2s times s. Because this length is 2s, I need to square the 2 and the s. So I'll go ahead and process that next, actually. 2s times itself, 2 times s times 2 times s, or 2 squared times s squared. Well, 2 squared I know. It's 4. S squared I don't know, so it's going to hang out. But I've got a like term here. I've got an s squared on this side too. So since I have a like term there, I can make a zero pair. I can subtract this from this side and this from this side, and I get that x squared, if I have 4s squareds and I take one away, I get 3s squareds. But I don't want to know what x squared is. I want to know what x is, so I can square root both sides. Square root of x squared is x, and square root of 3 is 3. Square root of s squared is s. Now, I could write it like this, but it gets really easy to be sloppy about how far this goes over. So our convention is to always write the thing that isn't under the square root first, so that it's very obvious this s is not under the square root and this 3 is. Because here it's easy for the square root to just sneak over and grab my s. So what this means is, if I have a triangle that's a 30, 60, 90 triangle, so if I see a triangle that I have a right angle and I have either a 30-degree angle or a 60-degree angle, because by two angles get the third angle, 3 in a triangle, I can use this relationship to figure out my side lengths. So let's do a few examples with this triangle. So if I have, let's do some 30, 60, 90 examples. I know this is a 60-degree angle, and I know this side is 5. I can take a shortcut, and rather than using trigonometry to figure out my other two sides, which normally I could do, I'd be like, well, that's the hypotenuse, so adjacent over hypotenuse is cosine, and that'd be the opposite, and opposite over hypotenuse is sine, so I could use those. But I already know for any 60-degree triangle, this side is just going to be 2 times that side. And this side is going to be that side root 3. So I can just fill in my 5. which is what S is this time. And see that this side is 10, this side is 5 root 3. Sometimes I'm going to want to keep this exact. A lot of the time, actually, I'm going to want to keep this exact. Sometimes I'm going to want to do a decimal approximation. But I was able to very quickly fill in the rest of my triangle. Similarly, if I had a triangle that maybe didn't look immediately like those because it was this way, but I knew this was a 30-degree angle, and this side was 7, well, once again, that's 30, that means that has to be 60. It's a right triangle. 30 and 90 tells me that one's 60. So this is my other leg. That'd be times root 3. This one would be 2 times. So 7 root 3, 2 times 7, which is 14. And again, I was able to very quickly calculate this triangle. Sometimes they may not give me the side that's the very easiest to deal with. They might give me this side and tell me that this side is, oh, well, let's make it kind of easy. I'll pick an even number, 12. Well, if this side's 12, then I know that that's equal to 2 times 6. So that means this side is 6, and this side is 6 root 3. Again, I would have needed to know one of these was 60 or 30 to do this trick. It doesn't work for just any triangle. So it is much faster if you have a 30, 60, 90 triangle to use this trick. This side is obviously a little harder to deal with unless they give you something with a root 3 in it. If they give you a side length with a root 3 in it like this, that is a strong hint. It's probably a 30, 60, 90 triangle, so look closely, and if it is, you can just pull that root 3 right off, and then you know your side length. So that is a 30, 60, 90 triangle.